Okay, folks, so then this next learning goal, we're going to connect the Gibbs free energy and equilibrium, which I think you've done in a lot of your other classes, so there should be some familiarity here. So if we think back again to this very simple equilibrium of A in equilibrium with B, we can write the total differential expression of dG of this reaction, which we've done previously, and it goes as the following. The chemical potential of A times its change in number of moles plus the chemical potential of B times its number of change of moles. And then now, using this whole extent of reaction quantity that we just discussed, we recognize that this becomes negative mu A times the quantity dZ, right, which was the quantity dNA, plus positive mu B times the quantity dZ. Okay? And because now that extent of reaction is the same for both of those, I can collect like terms, and just rearranging algebraically, this becomes mu B minus mu A times that quantity dZ. So all of that equals dG. And now noting this partial derivative over here, right? If I divide both sides by dZ, then I can see the delta G of a reaction is just simply the chemical potential of the products minus the chemical potential of the reactants, which we have established in previous discussions. Okay? So now, taking a look at this figure right here, where we've got extent of reaction on the x-axis and the Gibbs free energy on the y-axis, we remember that if delta G is negative, then we have a spontaneous reaction. If delta G is greater than 0, then we have a non-spontaneous reaction, spontaneous. And of course, if delta G equals 0, we are at equilibrium, all right? So if we take a look at this figure here, and let's suppose we're starting right here at pure reactants. We can see in this figure from this calculation, presumably of mu B minus mu A, that that would result in a negative quantity. So the reaction proceeds spontaneously in this direction. Now, as you can see, we get to this certain point where delta G has leveled off. Now we have attained equilibrium. That says equilibrium. Let's try that again. Equilibrium. I did not have to take a spelling test to get a PhD in chemistry, thank God. Okay. And as you can see, once we're at this equilibrium, it would be non-spontaneous to move forward. So at that point, we're locked in. And if you recall from your general chemistry and some of your other classes, for this simple reaction, we could write the equilibrium constant as the concentration of B over the concentration of A. So we'll put some more formal definitions on that and how we get to that expression. But just reminding you, right, we can write the equilibrium constant as concentration of products over the concentration of reactants. So, well, what if we were to reverse this reaction, right, and think of it in this way? Well, now if we were starting with B, we can see to move in this direction, it would still proceed spontaneously going in the reverse direction, and it would still then hit that delta G of 0 at the same position. So it's reversible, right? Doesn't matter which way we go, we will still hit that Gibbs free energy of 0, and thus we will be at equilibrium, okay? All right, that's all that I want to say in this learning goal, and we'll pick up with this in the next one. I'll see you then.